Hello, I am Dr. Anubha Gupta from ABES Engineering College, Ghaziabad. I am presenting lecture series on quantum mechanics. This is the part 5 of lecture series, and in this lecture, topic to be covered: particle in one-dimensional box, numerical problems based on particle in one-dimensional box. Under particle in a one-dimensional box, I present about the eigenvalues of a particle and the wave function of the particle which is confined in a one-dimensional box. This is the one-dimensional box of the length L. So let us consider the case of the particle of mass m, which is moving along x-axis between the two rigid walls at x is equal to 0 and at x is equal to L. The particle is free to move between the walls because no force is acting on the particle. So potential energy V is 0 inside the box. But the potential energy is infinity uh, at the walls. So the particle is the potential energy V for the particle is infinity outside the wall. So we can say the limit, the function of the potential energy as a limit, that for x is equal to 0 to L, x is equal to 0 to L, potential energy is 0. But at x less than 0 or at x greater than L, potential energy is infinity for these walls. So for the region, this problem is solved with the help of Schrodinger time independent equation. For region 1, Schrodinger time independent equation is del 2 psi over del x square plus 2m upon h cross square E psi is equal to 0. This is the equation number 1. And 2me upon h cross square is equal to k square. If this is the equation number 2, then it means del 2 psi over del x square plus k square psi is equal to 0. This is the equation number 3. This is the second order differential equation, and let the solution of this equation is psi is equal to a sine kx plus b cos kx. This is the solution of equation number 3. A and b are the arbitrary constant which can be calculated by applying the boundary condition. The boundary condition is that psi is equal to 0 at x is equal to 0 and L. Means at x is equal to 0 or at x is equal to L, particle cannot exist due to infinity potential. So it will be the psi wave function is 0. Now, psi is equal to a sine kx plus b cos kx. At x is equal to 0, psi is equal to 0. After applying this boundary condition, a sine k0 plus b cos k0. 0, a into 0 plus b into 1. It means if we want left hand side as 0, this is 0 plus b, which gives that b is equal to 0. It is only possible that the result of these two sum is 0. It is possible only when b is equal to 0. It means the wave function for this problem is a psi is equal to a sine kx. Now we will apply another boundary condition to determine the value of constant a. So another boundary condition is at x is equal to L, psi is again 0. So psi is equal to 0 A sine KL. So 0 is equal to A sine KL. So the product of A sine KL 0, A cannot be 0. Otherwise, this whole function, the solution becomes 0, which is not possible. It means sine KL is equal to 0, which shows that KL is equal to n pi. But already we know the constant K as a, this is the from the equation 2. K square is the 2me upon h cross square. So it become 2me upon h cross square L square is equal to n square pi square. So the energy E become n square pi square h cross square upon 2ml square. The all factors are in this energy are constant: pi, h cut, 2, mass, length of the box. It means this energies depend on the integer n, where n is equal to, here n is equal to 1, 2, 3. N is 0 is not possible in a quantum mechanics. So the energy values are En is equal to pi n square h square upon 8ml square. When I put h cut is equal to h upon 2 pi. This is called eigenvalue for a particle in a box. En is equal to n square h square upon 8ml square, where n start from 1, 2, 3 and 4. N square h square upon 8ml square. En is called eigenvalues for a particle in a one-dimensional box. If n is equal to 1, it is called ground state energy. It is called ground state energy. So ground state energy is n is equal to 1. It is a h square upon 8ml square. N is equal to 2 is called first excited state. First excited state. And it become E2 is equal to 4 h square upon 8ml square, which is equal to 4 times of E1. E3 is equal to 9 h square upon 8ml square, which is 9 times of E1. And in terms of, it means particle in a box has discrete energy levels. This is 0 to L length, and the energy levels at this point is E1, and this is the E2, 4 times of E1. This is the 9 times of E1, E3. This is for n is equal to 1. This is for n is equal to 2. And this is for n is equal to 3. Still, we did not calculate this A. This A is still pending with the help of boundary condition. So we will determine the value of A with the help of normalization condition. We can find the value of this A because wave function psi is equal to still A sine kx. And we know what is the K here. K is something n pi by L. So I can write psi as A sine k n pi by L. As a, in place of k, I can write like this. And we know normalization condition is that the probability of finding the particle in a given region is 1. So it is a psi square dx is equal to 1. This is called the normalization condition. So 0 to L A square sine square n pi x upon L into dx is equal to 1. 0 to L a square. Sine square x integration can be solved as 1 minus cos 2n pi x upon L upon 2 into dx upon 1. So taking the integration of 1 with respect to x, it is a x minus sine 2n pi x upon L 2n pi divided by L. By lower limit is 0, upper limit is L, and by putting the value of this L, and if I put L here, L will be cancelled out and become L, and this is going equal to 1. So from here I can calculate the value of A as this. It means the wave function psi is become A sine, in place of A sine n pi x upon L. This become, in place of A, I will put under root 2 by L sine n pi x upon L. It means wave function. This is the wave function for a particle in a box for n is equal to, where n is equal to 1, 2, 3. So for ground state, n is equal to 1, which is equal to under root 2 by L sine pi x upon L for n is equal to 1. For n is equal to 2, it is a psi 2 under root 2 by L sine 2 pi x upon L. Similarly, psi 3, psi 4. This is the psi 1, representation of psi 1 for energy level E1. This is the energy level E2 and this is energy level E3. This is the representation of psi 1 and this is the representation of probability density psi square. Because psi square cannot be negative, so this portion will be on the upper side and it become positive. This is not, it is not possible that psi square is negative, so this reason become positive. So this is a particle in a box. So I am writing it again. Eigenvalues are n square h square upon 8ml square, where n is equal to 1, 2, 3 are called eigenvalues for a particle in box. For a particle in box. It means energy for a particle in a box is in discrete manner, not in a continuous manner. And the wave function associated with the particle is under root 2 by L sine n pi x by L, where again n is equal to 1, 2, 3. It is called eigen wave function. Eigen wave function for a particle in a box. In a one-dimensional box. A one-dimensional box. So these are the eigenvalue and eigenfunction. Now I am going to discuss the numerical on these two on this formula. An electron is bound in one-dimensional box which has width 2.5 angstrom. It means L is 2.5 angstrom in meter, 2.5 into 10 to the power minus 10 meter. Calculate the two lowest permitted energy values of the electron. Two lowest means n is equal to 1 and n is equal to 2. N is equal to n square h square upon 8m L square. For n is equal to 1, it will be E1 is equal to h square upon 8m L square. And it is E1 h square means 6.6 into 10 to the power minus 34 square divided by 8 ml square. 9.1 into 10 to the power minus 31 and the length is 2.5 into 10 to the power minus 10 square. This is the E1. So solve this E1 and E2. After solving this E1 and E2, we will get this value is 6.04 electron volt. For converting in electron volt, we will divide it by 1.6 into 10 to the power minus 90. And we know that E2 is 4 times of E1. So it is a 24.16 electron volt. This is the answer for E1 and E2. Question number second. Calculate the energy difference between the ground state and first excited state for an electron moving in one-dimensional rigid box of length 2.5 angstrom. Again, this is the problem from the one-dimensional box. We know energy eigenvalues for particle in a box is n square h square upon 8ml square, where n is equal to 1, 2, and 3. But between the ground state and first excited state. So for ground state, n is equal to 1. It is a E1 is equal to h square upon 8ml square. And n is equal to 2 for the first excited state. E2 become 4h square upon 8ml square. And the difference, energy difference, E2 minus E1 is equal to 3h square upon 8ml square. We find the value of 3h square upon 8ml square. 3. In place of h, put 6.6 into 10 to the power minus 34 whole square divided by 8ml square. 8. 9.1 into 10 to the power minus 31. Length is the 25 angstrom, which is the 25 into 10 to the power minus 10 whole square. So first of all, we will solve in terms of joule and then divide with the 1.6 into 10 to the power minus 19, which give the answer which is a 0.18 electron volt, around 0.18 electron volt. This is the answer, or this is the difference between the two energy values. These are the references of my lecture, Concept of Modern Physics by Author Weiser, Solid State Physics by S.O. Pillai, and Engineering Physics by S.K. Gupta. Thank you for patience listening.